I'll edit this part out while I wait. Okay, I think that's good enough. Hopefully this. The first thing I always do, because every video needs to give credit where credit's due. These people over here, I give all the credit to because they taught me everything I learned here. Last time, we finished up by doing this Taylor series expansion over here. As you can see, it's a beautiful expansion. It shows you what it is, but it got cut off last time. So, yeah, so what's happening here is that anywhere that has dx by a higher order over here, which is dx squared, I disappear because it is beyond the capacity of it being, linear. Because as you know, we love linear. Linear is the best. Now, the next thing I will explain, I don't think I explained, is Taylor series properly. So I just showed you this Taylor series over here, which is beautiful over here, but that doesn't really explain how I got this form. And I don't think I've ever explained it. So basically, let's see if I can write it here. Taylor series is, first of all, how you write Taylor series, if I remember correctly, is f of x, like f of x, equals summation of infinity to n equals 0, right? F n of a parentheses by, which a equals 0 in this case usually, ni, and then this is x minus a n, right? I'm pretty sure. So what we do is claim this next, right? Right, this is what I did. Yes, we did that. Yeah, yeah. And then I believe this is why we have f1, right? Which is just 1, which is just x. So this is 0 actually. Start with 0, so 0. So we have this, right? And then we have the f differentiable, which is d dx, right? Now, the one thing is this over here needs to be dx, right? Right? So we plug this into here because this is what's happening is understanding that it is we go from x, which is x equals 0 or something, and then we plus dx over here. So we have a x dx over here. So we claim that a equals x plus dx. So that way dx shows up. Okay. I hope that helps in one way or another. Yeah, I think that's all right. That's good enough explanation for now. I'll just leave it there. There's no point in deleting it. We're moving on now. To get the idea that the mass flow rate is constant. I don't think we have done that last time. We finished up the Taylor series expansion, but we never explained what that really entails us saying. Well, that entails us saying that we have a rho u, right, from the beginning phase. Did we do shockwaves properly? I don't think we did, so we'll go back to it later. But first of all, we need to understand that this is our beginning over here. Why is it so interesting? I don't know why my cursor is not acting correctly, but we understand that this is true. And then if I get the definition, let me just double check that nothing is anyways, anyway, we're changing this to a plus dA. Yeah. So we're doing, I believe it was a density u parentheses a, no, x plus dx right here. And then we're getting the differential of it. Basically, we're subtracting it. Why we're subtracting it, I didn't explain, I don't think. It's a controllable body, which we have a normal surface like this, a normal surface like this. Why do we not have penetration over here is a good question. Now, if you know anything about, actually, I should just tell you this. You don't know. I'm assuming that the audience doesn't know it. Basically, you assume that it's following the same direction like this. It's a no penetration rule. Euler has no penetration no matter what. And then the boundary layer also would work, but that would also indicate over here if we did do boundary layer, which it doesn't matter here because it's supersonic, hopefully. I hope this is supersonic. If not, then there are some problems with that, but I don't know if I really should have. But if even if this boundary layer is like this, it should be just going like this because it's going super fast, and there shouldn't be any case where there's turbulence, right? And we'll see. Oh, there might be actually. I'm wrong because thinking about it, there is a rate, but that's when we're talking about not fast flows, and I don't need to talk more about it. I'm talking too much. Anyways, so we know this, so we could actually just ignore the middle part, right? So the velocity is going inwards over here, so that this is negative. And this is going outwards like this, continuous, so this is positive. So what that indicates is a rho u x plus dx minus a rho u parentheses x. Now the question is, so why can't we just assume linear? Um, I could give you two ideas for that actually, but in reality, in most cases, linear is easier to deal with when you do integrals, is my headcanon. But in reality, it's probably due to the higher orders not mattering because of the in numerics I learned that further faster you go down like this, it goes to 0. So dx squared just goes down to 0 faster. And if you have something higher order, why not use the higher order version if you could get it? Now that breaks down that if you do a Taylor series at some weird places, it does have some weird issues, but that's not here. A density u, and then it's x plus d dx a rho u dx minus a rho u parentheses x. This goes cancels out, and we are left with this equals 0 because of our continuity equation as we discussed over here. I remember where I put it. Continuity, beautiful continuity over here. Now, what does dx a rho u dx equals 0 mean? It means that the m dot equals the constant of basically rho, which is going to be a function of x in this case, right? And then it's going to be a, which is a function of x definitely, and then u as a function of x will equal the constant 1. So what that means is if a is increasing over here, the a is increasing. This is the only thing it says. U and rho needs to change. That's all that it says so far. I don't see it saying anything more different. If I'm not wrong, yeah, that's the only thing I see. Hopefully I'm not wrong. I'm pretty sure it's okay. We'll see if I'm wrong. Uh, pretty sure that's how you say it. And you'll see this in nozzle and stuff. But next we'll go to what we call the integral form of conservative equation. So there's no reason for me to think any more than just do here, I think. If I remember correctly, we're doing it one way, right? We're doing it like this. So we have u over here, but the outward end is this way and outward end is this way. So what that really means is that this is going to be v, but the v vector is v, and then it's going to be tangential, and it's going to be minus negate, so minus negate, I believe, right? And it's going to be area in the gate, parentheses, x plus the, no, x, that's a minus, and then it's going to be plus a u, and I don't know if u is different. Yeah, oh yeah, u is different, but u is categorized by the x plus the x, so we should be fine over here. So in that case, we have everything. Now, now here's the thing. Note that the tangential and the velocity is the same, so we can just get rid of this with u squared instead. And now my whole entire writing is getting confusing, so let me just clean a little bit. Um, Now the pressure is gonna be harder, so I'm trying to do this first. So we're gonna have rho, right? U squared, then a, and this could be x plus dx, right? Minus a rho u squared parentheses x, right? So this will give me equal to uh, this left side there. So the left side is changed into, okay, it's going to be the same Taylor expansion, and I'm not doing that again. So we're just going to do a rho u squared. But in reality, for this one, it's a little more confusing. Now let's just stick with the first one. We have p and a direction, right? Which is a, right? We get a from the surface. X plus dx, and then we have the plus p a x, right? Oh, minus, right? It's a minus. So this is minus, this is plus because of the. Okay, what does that give me? This gives me d dx p a dx, right? As you know, that is true. That's what we get. Now, the thing is, this isn't everything, although. This is impossible. What do you mean by impossible? Well, if this was the case, it would imply that the derivative, which it leaves everything, which is p plus dp. Let me just look at this. A plus dA, right? It's PA plus A dP plus PdA, right? And it's going to be parentheses, it's going to be minus over here, and it's going to be plus PA. Now you get rid of this, and you see this thing over here, which is basically going to turn into that. Now, is that everything? No, 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 because there's nothing to move the pressure. Um, now, yeah, because it's a differential, so you need a plus PdA. Now, where does the plus dA really come from, basically? It seems like it looks like something like over here, maybe. But in the end of the day, it doesn't really show where it came from because this is obviously used for this one. There's an extra plus PA. Now, how this is kind of looked at is because there's no dot product that this is occurring, and this needs to be appearing because pressure has to appear somewhere. So why does this appear actually? I originally thought it was because of this idea that this is a main body. So we already have pressure moving like this way already. So you need pressure that's not dependent on differentials. That's what I'm trying to say. No, the original differential, which is dsd. Anyways, that's what my conclusion has come up with, but there probably is a better conclusion here. Yeah, yeah, there probably is a better conclusion. I yet to see a better conclusion. Someone smarter than me can probably figure out something better than what I have thought up of. But that's my headcanon right now. But the easier way in reality, it must be due to Taylor series. Because what's happening here over here is that in reality, what you're doing is dx over here and dx over here, right? Beautiful, right? But that makes something that's going into like many directions. Only look at the dx change. So the PdA must be the other changes from the differential. So if you think about it, the pressure is like this, and there's a dA over here. So in reality, the other changes that we haven't really covered by this dA is just pressure, because pressure is a scalar, is making this happen. Now, that's my headcanon. I might be wrong, but that's what I have concluded. Now, the next thing is tau at the end, which is interesting because, this is like this, right? So basically, we have to define it as tau w, which is why tau w, and it's going to have just dx. Now, that is a pretty interesting result. So in total, what we get from this is basically, If I have a better explanation later, I will definitely come back to you and explain it in a better way. But uh, a minus, and then it's going to be, because it's minus plus, p a dx d, I already have that. So it's equal to tau wl dx plus p dA. Okay, so we have this now. And this, so we can actually simplify a bit more. As you can see, I'm not screenshotting anymore because it's taking a long time to screenshot. I don't know what the internet is up, but the internet is like taking forever to screenshot things, which I don't appreciate, so I haven't been doing it that way. So the dx goes here, dx goes here. So this is tau, this goes away, and this goes away. L plus P dA dx. Yeah. Yeah, you probably noticed I haven't been doing all the screenshotting of the whole text because for some reason my this Wi-Fi is not working correctly. Anyways, we have all that down. Now we can move on to the next step, which is basically the energy, which I probably should find the energy equation, but uh oh, energy equation is over here. I would have screenshot this, but I guess I'll just handwrite it because I don't think the screenshot is working. As of late, I don't know why. Probably because this one whiteboard is like 12 pages long. In reality, there's like 12 slides here, and the whiteboard is not really working well. But anyways, integral d dt, we have d dt, and the volume integral. So again, we can make it triple if you want. It doesn't really matter. I don't think I never seen anyone complain about my. Yes, I'm just gonna write it the way Dr. Sanchez does because it is easier than dealing with the other way, which is a triple integral. Yeah. Always make sure it's a scalar for energy. If there's some kind of vector nonsense, you did something wrong. And yeah, this is the one equation I really don't have memorized. Energy equations is the one that I don't remember. And if I mean, I remember the differential one, but the integral one, no, I don't really remember this one because it takes a while. I hope I memorize it soon. I'm not denying that I don't want to memorize it, but this goes away, right? Anyways, wow, this is actually a little bit interesting. So we know that this is the same way. We have the same like contusions like that. So we have to know n, and n we know that it is, and the q goes like this too, really. So q is this Fourier's number over here. So we can just do ql over here, and then the dx, right? No, we just leave it be. Really? No, it has to have dx because you're doing a small layer over here. So it's multiplied because it's L times dx. That's the area. And then over here has hmm, and u is just u. So it's rho u, right? Am I feeling here? No, I don't think so. It's going to be d dx h plus u squared divided by 2 dx equal q wall L dx plus, I think you could just, I don't know what to do with this one. I think it's just going to have to be, looks like the professor does it this way, so we're just going to keep it like this. But from this, we can divide the d, oh, there's a dx over here, definitely, because you're doing volume. So we divide by dx over here, I think. So it's rho u a d dx h plus u squared divided by 2 equal q w L plus q ch plus q radiation, dot dot. Now, my question is this correct? Part over here is a tau is basically almost zero because we're doing a like that. So unless it matters with boundary with the boundary, we don't care. I think that's the reason why. That's the only justification I could think of for why that's got rid of. Next video will be on frictionless. We just did momentum and energy.